Welcome back to this lecture on recurrence relations. Now remember that to solve a recurrence relation means finding a non-recursive or closed-form formula for the sequences that satisfy the recurrence relation. And remember that we described the iterative method to solve recurrence relations. Now the problem with the iterative method is that it's not really an algorithm. Remember, one of the steps is to identify a pattern. And this step requires insight. It cannot easily be programmed. It's not algorithmic or mechanical. So the iterative method is not really an algorithm. So it would be nice if we could come up with an algorithm to solve recurrence relations mechanically. Well, that is not possible in general. However, there are some classes of recurrence relation that can be solved by specialized algorithms. And in this segment, we're going to study one such class of recurrence relations. These are called linear homogeneous recurrence relations with constant coefficients. Now, I'm going to abbreviate this LHRRCC, and since the abbreviation is pretty much as hard to say as the full name, I'm going to pronounce this as LHRRC. So, a LHRRC is a special kind of recurrence relation, meaning it's a recurrence relation with a special form, and here are the constraints that a LHRRC must satisfy. First, a LHRRC must be a recurrence relation. Of course, that's the double R in the name. Now, a recurrence relation has a generic term a sub n, which is defined as a function of the previous terms, a sub n minus 1, a sub n minus 2, a sub n minus k. So, the first constraint we want to put on the LHRRC is the L here. That's the linear part. So, a linear recurrence relation must satisfy the following constraints. The previous terms that a sub n depends on must be raised to the first power. So you don't have any squares or third power or fourth power, just the power 1. That's the linear part of the definition. Second, the previous terms are multiplied by coefficients. These terms can be added or subtracted to each other, but they cannot be multiplied together. And finally, these previous terms cannot have any functions applied to them. They are just added or subtracted directly. You can't run them through a function. So, this is the definition of a linear recurrence relation. We're going to give some examples later, but first, let me describe the other constraints on LHRRCs. The second constraint is that the coefficients, these coefficients here that are multiplying the previous terms, must be constants. So the constant coefficients is the double C part in the name. And finally, we must explain the H part, the homogeneous. And this just means that only previous terms of the sequence can be included in the definition of a sub n. So a sub n cannot be a function of anything else. So this concludes the definition of a LHRRC. I'll say it one more time, a linear homogeneous recurrence relation with constant coefficients. Now let's consider some examples. The first one that we've seen before is the recurrence relation that is satisfied by the Fibonacci sequence. So let's check the conditions. A sub n is defined as a function of the two previous terms. These terms are not squared or raised to any power other than 1. They are added together, not multiplied. They are not run through any functions. They are just added directly. The coefficients in front of them are constants. In this case, the coefficients are 1 and 1. And nothing else is added beside those two previous terms. So this is a LHRRC. Here is a slightly different one. The only difference here is that the coefficients are 3 and minus 2, Everything else is the same. Since these coefficients are constants, they don't depend on n, this is definitely a LHRRC. And as a third example, let's consider this slightly longer one. In this case, we have three previous terms, n-2, n-3, and n-7. The coefficients are constants, 10, 2, and 17. Nothing else violates any of the constraints in the LHRRC definition, so this is definitely a LHRRC. Let's conclude this segment by discussing a few counterexamples, that is, recurrence relations that are not LHRRCs. So notice in this recurrence relation, a sub n depends on different previous terms. There's nothing wrong there. Some of these terms are added or subtracted together, that's fine. And notice the fact that a sub n minus 2 appears twice is not necessarily a problem, assuming that you could rewrite this recurrence relation by combining these terms. But in this case, we can't because we notice several problems. First of all, this term is not linear because it is raised to the power 2. That's not allowed. This term is also not allowed because you're not allowed to apply a function, in this case the logarithm, to one of the previous terms. And the third violation of the definition is that these two previous terms are multiplied together, and that's not allowed. So let's look at a second counterexample. This one is almost a LHRRC. The only problem is that its coefficient here in front of the a sub n minus 2 term is not a constant. It depends on n. So this is not a LHRRC for that reason. And finally, this recurrence relation is not a LHRRC either because of this minus 8. Notice all of the terms here satisfy all of the constraints of LHRRCs. However, the last constraint, the homogeneity constraint, states that all you can do is add and subtract previous terms to define a sub n. You're not allowed to add or subtract anything else. So you're not allowed to subtract a constant here like an 8. That's a non-homogeneous recurrence relation, and therefore it is not a LHRRC. So make sure you are very comfortable with the definition and the constraints that must be satisfied for a recurrence relation to be a LHRRC. In the next segment, we're going to describe an algorithm to solve this type of recurrence relations.